This is problem number 13 on homework 5, and it has a resistor, capacitor, inductor in parallel. And here are the impedances of those components. So impedance of a resistor R, impedance of a capacitor is minus J 1 over omega C, impedance of an inductor is J omega L. So this is kind of a complex problem because you have these things in parallel rather than series like we had in the other problem down here. So I'm going to work it through there with you. I want you to realize along the way that I'm not going to have a complex problem like this on the exam, but I do want you to work through this on the homework set. So I'm going to go through it there with you, and many of the elements here will help you prepare for the easier problems that you will see on the exam. So when you have components in parallel, you add them like this, the sum of the reciprocals over in the denominator like this, so 1 over the sum of the reciprocals. And then I just went ahead and put in the impedances of the resistor, capacitor, inductor, so 1 over R. And then I flipped this thing right here and got that, and then I did 1 over that and got this here. Then what I did was I multiplied top and bottom by J here, and so I got J squared on the bottom, canceling out that minus sign, giving me a plus here. Multiply top and bottom here by J, and then again I get a minus J from the J squared in the denominator, and that's J over omega L. Alright, so the next thing you want to do is try to find a way that you can get the complex expression, because this is 1 over a complex number, but we really want a complex expression so that we can get the polar expression after that. So the next thing you can do is factor out the J to make it look more like a real number plus a complex, plus an imaginary part like that, but it's still a reciprocal. To make things easier, what I decided to do is call this 1 over R, just call it A for simplicity, and then everything in parentheses I called it B, so it looks like a real plus an imaginary part. And so I made a note off to myself off to the side that A is equal to 1 over R, B is equal to everything inside of that parentheses right there. Keeping the J, of course, because that's showing me the real plus the imaginary part. Now the way that you can get this so that it's in the end a real plus imaginary number is you multiply it by what is called the complex conjugate of the denominator. And all that means is that you take this thing right here and you put it over here and you put a minus sign instead of a plus right here. So whatever sign that is, you just change the sign. So this thing that's in the denominator right there is the complex conjugate of this right here. And so it's legal mathematics to multiply top and bottom by the same thing, just like we did up here. You know, we were doing J on the top, J on the bottom, like that, right? So you do the same thing here. Multiply top and bottom by complex conjugate. And the cool thing about the complex conjugate, I just called it cool. I don't know why I did that. So you get the A square like this. The cross terms cancel out, so you don't get anything from doing A times this and A times that. They cancel out using the FOIL method, if you will. And if you multiply this times this over here, you notice that you get a minus J square B. And the J square becomes a negative 1. Oh yeah. So I guess this really should be positive. Let me think about that just a minute here. So B times B right there, B squared. And then J times a negative J is a negative J squared. And J squared is a minus 1, so that becomes a plus. Interesting. Okay, so then got that there, and I left this as it was on the top, complex conjugate times 1. Oh yeah, it looks like I already knew that. Except for right here, I made a mistake. That should be a positive right there. I divided it into 2 parts. So I took A divided by the denominator, and then the minus J, B times the denominator again. I just wanted to show you that this now has the form of A plus J, B. That's the real plus the imaginary part. And we're so used to handling or dealing with, finding the magnitude of a complex number like this. And that means you just take the A component and the B component, square them, square root. And I know what those components are. I got them right here. So I squared the A, squared the whole thing in the denominator, plus minus B squared all over this right here. And then I got combining, common denominator here. I get A squared plus B squared over A squared plus B squared squared. So then one of those squares cancel out, and I get 1 over A squared plus B squared. At this point, you can go back to your definitions of A and B and actually get a value for the resistance in ohms. You might be wondering, why do we do all that again? Why were we finding the magnitude? Well, you come back over here, and remember that the polar form here is you got an angle, and so this is the magnitude that would go right there. The value that we got just right there from doing this, the magnitude of the equivalent impedance right there is what goes here. So then all we got to do now is find the direction, which would go right here, and that would be in degrees. Remember how to handle that? Inverse tangent of the B component of this thing right here. So basically capital B over A. And so there's my B, which is this. There's my A, which is that. These denominator terms cancel out, and I get the inverse tangent of minus B over A. Remembering what my definitions are from up here, plugging in actual numbers, and so I'll get a number here in degrees. I know that this is a complex problem, so just hang in there, push through it. You can do it. You got to do it 3 times. It will reveal something to you. You'll actually see this is something called a notch filter right here, which filters out an unwanted frequency. This one right here is called a bandpass filter. It only allows through certain frequencies. So there's some really cool applications when you can get past all the complexity and see the applications of these circuits. All right, I hope that helps. See you soon.